Okay, good afternoon, everyone. Thank you for taking the time to make it to today's session. My name is Daryl Saraspe. I'm an engineer with Midas. So I just want to do a quick sound check just to make sure everyone can hear me. So if you can hear me all right, just please raise your hand through the screen. Otherwise, you can type in the chat box if the audio isn't loud enough for you. Okay, so I see that pretty much everybody has their hand raised. So over the course of this session, currently I have all of you muted, but if you have any questions in the meantime, you can enter into the chat box, or what you can do is you can save your questions for later on. I'll send you my email address, and you can email me then afterwards, and I can give you more detailed responses. So once again, thank you for attending today's session. This is the first session of an 8-course series. This will be just an introduction of numerical analysis for geotechnical applications. So we won't be going into anything too detailed today, but we will be giving an introduction to numerical modeling as well as how it can be used in conventional geotechnical projects. Okay, so first I want to go over the learning objectives. So at the end of this course, we'd like all registrants to have an understanding of numerical analysis in the geotechnical industry, why it's important, why it's relevant, and how it can be used for projects that you're working on. Next, we'll be going over an overview of theoretical principles, both for conventional and numerical modeling. And then also we'll be going over comparisons of conventional methods for geotechnical design. Okay. Okay, so here's just an overview of what we'll be going over today. So first we'll go over just the basic background, categories of geotechnical problems, conventional methods, just a review of knowledge that you should already be familiar with. And then we'll go into the application of numerical analysis itself, why exactly we need it, what certain design parameters that we can obtain from it that are unique and helpful to us as engineers, and also certain considerations of numerical analysis. Okay. And then next we'll be going over numerical analysis in geotechnical engineering. So we'll be discussing how exactly numerical analysis can be applied to geotechnical projects, and we'll go over several of those project types over the course of that session. And then last but not least, we'll be going over case studies or certain projects where numerical modeling was used successfully for geotech projects. Okay, so once again, the chapter 1, this is just the background. So we'll go over categories of geotech problems, approaches to solving these problems, then also comparisons of various conventional methods, certain shortcomings and advantages of each one. Okay, so first let's review geotechnical structures. So I'm sure all of you are familiar with the structures here on the left: foundations, retaining walls, deep excavations, dams, etc. So over the course of geotechnical design and analysis, these are various structures that you'll be designing for and that will be used for the scope of your project. And as far as related geotechnical problems, so with every geotech project, certain problems or certain things need to be taken into account. So for example, with a foundation type problem, you might have to take settlement, earth pressure, or the stability into account. The same principle applies to retaining walls. You may have to take seepage, consolidation into account, so on and so forth. So as you can see, there are various sort of combinations of structures and problems that you may have to deal with as a geotech engineer. And I'm sure you all have certain methods, conventional methods that you use to take care of these problems. So what we'll do later on in this presentation is we'll describe how specifically finite element analysis can be used to supplement certain methods that you already have. Okay, so there are 3 major forms of solutions towards geotechnical problems. So first and foremost, there are closed form solutions, or conventional or analytical methods. The main sort of characteristics of closed form solutions is that they require assumptions. So for example, you might have certain project geometry that can be simplified just to expedite the work process. Certain simple geometry that doesn't need to be analyzed in detail. So for example, Terzaghis 1D consolidation as well as foundation settlements are 2 very efficient and very successful examples of conventional methods. Next we have numerical methods. For example, the finite element method, finite difference method, discrete element method, and the boundary element method are all examples of numerical methods. And the main focus of this course will be finite element method or numerical modeling. How the finite element analysis. Okay. Okay, so sorry about that. I didn't have everyone muted here. Okay, perfect. So as I was saying, the main sort of focus of these sessions will be the finite element method and how specifically it can be used to supplement conventional solutions as well as empirical methods. And last we have empirical methods, which require the use of field instruments and monitoring data. So essentially empirical methods are calculated through the use of equipment that's taken out into the field, and you take these equipment, you take your measurements, and then you take certain soil samples maybe back to the lab and get your data through that method. So once again, all three of these methods have various strengths and weaknesses, but when used together, they provide sort of the ideal sort of solution set towards any type of geotechnical project. Okay, so first we'll discuss just the basic theoretical background of the finite element method. So the primary characteristics are embodied within the stiffness matrix. This equation is it's sort of at the heart of finite element analysis. F equals K times U. F equals the loads, which are known. K is the project geometry as well as the material properties of the elements. Material properties of your soils as well as the material properties of your elements or structural elements. And U is to be determined, which represents your displacement. So U can be solved by using the matrix inversion method. So F equals K times U becomes U equals K to the negative 1 times F. That's how you determine your first nodal quantity. And also keep in mind that these stiffness matrices become more and more complex and more detailed with larger geometry and larger scopes of projects. Okay, so once the displacement is calculated, then the stresses and the strains can be determined as well. So for example, once you have your displacement, you can calculate your strain based on this equation. And this is for 1D type geometry. So for 2D and 3D strains, the algebra would be a little bit more complex. And then after you calculate your strain, you can get your stress by multiplying the strain by the modulus elasticity. And then once you get your strain, you can calculate your factor of safety. So this is just something to give you a background of finite element analysis. I won't go into too much detail about this. But one of the main strengths of finite element analysis is it's very detailed. But one of the shortcomings is that it takes a lot of time to do these calculations, as you can imagine. For those of you who took any type of linear algebra or stiffness matrix courses, you know that it can take a long time to complete. But with numerical modeling programs, the work process is greatly expedited. Okay, so now let's talk about foundation problems. So as far as foundation problems, first let's talk about empirical solutions. So if you look to the right here, I'm sure all of you are familiar with these types of graphs where if you have, for example, your shear strength, you can calculate it. You can calculate, your bearing capacity just through referring to these graphs and depending on the type of soil that you're using. And these are all sort of calculated or determined through empirical methods. And then pile group capacity problem, Feld's rule, and the converse Labar formula, as well as block failure criteria, are all things that need to be taken into account when doing a group pile foundation. So if you look to the right here, as you can see, here we have just a cross-section of a group pile foundation. So one of the main things to remember is that a strength of group pile foundations is that it allows the foundation to distribute the stress over a larger sort of volume of soil, thus making the foundation more stable. So as you can see, when these three piles are placed together, the isobar is greatly increased. But another important thing to take into account is that when piles are grouped together, in the soil there would be areas of highly stressed zones because the individual isobars will cross. So with conventional methods, what is done is that it just simplifies the piles, and it doesn't really it accounts for a highly stressed zone, but it does through conservative analysis. So that's sort of one of the shortcomings of conventional methods, is that you'll get something that's safe, but it's very conservative. But with numerical modeling, you can actually account specifically for these highly stressed zones to create pile group foundation designs that are safe as well as optimized, or in other words, cost effective. And we'll discuss more into detail about how finite element modeling can specifically give you a sort of special or unique and useful results with pile foundations later on. Okay, so as I discussed, numerical analysis provides alternative to overcome difficult problems. So with more complex or higher end type projects, numerical modeling becomes more and more prevalent. And then it's very important to cross-check your results with field data as well as analytical methods. So that's another sort of concept that I want you all to get from this presentation, is that numerical modeling is very powerful, but it's not just going to replace what you already have. It's going to be something that can supplement what you're currently using, so that you'll have you'll be able to design with greater confidence. Okay, so slope stability problems. So I'm sure you're all familiar with the limit equilibrium method. Essentially what happens is a slope is divided into several slices, and then just using the laws of physics, we're able to determine the free body diagram. And then once we get the forces acting on each individual slice, using integration and various equations that have been tested, we can determine the strength reduction factor as well as the factor of safety. So the limit equilibrium method once again relies on simplifications of soil geometry, but it's very effective because it's very easy to do, it's very quick, and it's very good for conventional type projects. One of the shortcomings is that you can't really account for reinforcements. You just sort of have to over-design. And then also you can't account for deformation or changes in pore water pressure. So we'll discuss how numerical modeling can attack, or how numerical modeling can overcome those specific variables later on. Okay, so now let's discuss retaining wall problems. So with conventional methods, essentially you would design for these criteria here. For example, the design stem, the heel width, overturning bearing. Those are certain aspects of reinforced or retaining wall design that you can analyze just using simple sort of calculations that are based on physical laws. But when it comes to more complex aspects of retaining walls, the numerical method is essentially used. So for example, soil structure interaction with the backfill, construction stage analysis, failure mechanisms, and also effects on adjacent structures. These numerical methods would best be used to analyze or to calculate for these variables. So as I discussed earlier, conventional methods are really best used when combined with numerical analysis methods. That way you can design for any type of criteria that you need. And it's also important to note that the more, so for example, the deeper this reinforced wall gets, or the deeper your excavation becomes, the greater your soil pressure will be acting on this wall, in which case a conventional method, although you could design for that, you would still have a design that would be highly conservative, and that might, in the end, the project might cost more than it should if you just stick to the conventional method. Whereas if you were to start using numerical analysis, you'd be able to start to optimize your design. You'd be able to design with accuracy as well as cost efficiency. Okay, so excavation type problems. So first let's discuss conventional methods. The two analysis methods of interest are simple beams and continuous beams. And one of the main things to note is that these are suitable for shallow excavations. In other words, for smaller, more conventional, straightforward type projects, a conventional method could suffice because there are less variables to take into account. Okay, so then the earth pressure method. So the earth pressure method is used for deeper excavation type problems. So as you can see, it does earth pressure calculation problems, whereas if excavation gets deeper, the more earth pressure is acting on your wall or your support structure, in which case a conventional method would become less effective for it. So earth pressure methods, they're slightly more advanced, and they're used for deeper excavation types. As you can see, it says it's suitable for deeper excavations. It considers lateral earth pressure coefficients. So as you can see, one of the main sort of principles of this session is that as your projects become more complex or more high-end or more variables are taken into account, conventional methods need to be supplemented by the numerical modeling as well as empirical methods. So next, let's talk about soil structure interaction, which is specifically done with numerical analysis. So for example, if you had a project where soil structure interaction would become especially prevalent, say for example a high-rise building, a large warehouse, an industrial plant, projects of that nature, then soil structure interaction would become more prevalent because design codes require that you check for soil structure interaction. Essentially what soil structure interaction is, it describes or it calculates the behavior of a structural element that's directly in contact with the ground. So when structural elements are directly in contact with the ground, the behavior is unique, and it needs to be analyzed with what's called interface elements. And we'll discuss those in greater detail later on. Okay, so just a summary of what we've discussed. First and foremost, numerical modeling provides alternatives for difficult problems. It doesn't offer necessarily a complete solution, but it provides you with a tool that allows you to consider more variables. So essentially, numerical modeling would be able to enhance your tools or your skill set so that you'd be able to approach these difficult problems with greater confidence. We need mutual supplementation to obtain detailed results. So as I discussed earlier, the best approach for any type of geotechnical analysis would be to have a combination of empirical methods, analytical results, and as well as numerical modeling analysis. So once again, through numerical modeling, you can supplement your current sort of toolbox, and you'd be enabling yourself to obtain a richer sort of range of results that would help you to design more effectively, more productively, and to save money, save project costs. And it's an advanced approach that can consider more variables. So as your project becomes, as your project takes on more variables, as it becomes higher end, or as there are certain other things to take into account, numerical modeling becomes more prevalent. It becomes more useful. Okay, so there's no exact solution for geotechnical problems. So essentially what we're doing is that we're finding the best solution using everything around us. These tools that I mentioned, they're best used when the scope of the project is considered. And then even afterwards, you need to account for certain variables that the methods might not have taken into account. So just keep in mind that even though you may have solutions that you like, that you feel are favorable, it's not going to be absolute. There will always be certain factors that can't be taken into account. So it's really an estimation of what will happen as opposed to something that's perfect or ideal. Okay, so now before we continue, I'd like to just give you a quick quiz. I'll bring it up right now. It's a very simple quiz. It's only 3 questions, and I'll just pull it up for you, and then once you're done, just submit it to me, and then okay. So in this chapter, and will be discuss why specifically we need numerical analysis, certain things that are very unique about it that are useful to us, what we can obtain from it, how to utilize the design parameters. So certain things need to be taken into account for numerical analysis, and then also things to be considered. So certain things that are very unique about numerical analysis that need to be considered that you wouldn't normally consider for other conventional methods. Okay, so why do we need numerical analysis? First and foremost, there's no limitation in the modeling. So for example, if you have any type of like 3D geometry or geometry that's more complex that you wouldn't be able to model effectively with a conventional method, you'd be able to do that with numerical modeling. So just keep that in mind, that any type of geometry that you come across, it can be handled efficiently with numerical modeling. Okay, the stress-deformation relationship. So soil element stresses as well as structural stresses and deformations can be analyzed in details with numerical modeling. So this becomes more and more prevalent for certain projects where you would need to, for example, calculate the displacement, for example, settlement type projects, retaining wall projects for deep excavations, etc. Soil structure interaction. So for large, heavy foundation type projects, soil structure interaction is essential. A lot of design codes require, depending on the region you're in, that you have to run a soil structure interaction analysis. And this can be very easily done with numerical modeling. And then efficient parametric studies for optimum design. So for example, if you have a certain design that you want to run that you find checks out, there might be certain instances where you find that you want to run different sort of variations of that design to see which one would be more cost effective. So through numerical modeling, you'd be able to run parametric studies very quickly, much faster than you would through maybe like a conventional method. And then reflection of construction stages. So this sort of links back into parametric studies. So for larger scale projects or for projects that require sort of staged excavation or constructions, you'd be able to model multiple stages with numerical modeling. And then various analysis types can be considered. So I'm sure many of you have maybe encountered certain projects that required several analysis types. For example, maybe an embankment type project, you need to analyze the seepage as well as slope stability, or retaining wall projects that also need to require that are built by basins. You would have to run sort of several analysis types in order to complete your project. So with numerical analysis, you can run all of these analysis types very efficiently. And then various constitutive models for soils. So soil behavior is very unique, and it's also sort of complex. So there are dozens of constitutive models that monitor or that calculate the behavior of soil. So the numerical modeling, you can use various constitutive models for your project instead of relying on just one or two. Okay, so let's do a quick case study. This is the Carsington Dam in England, or just a sort of an image of the Carsington Dam in England. And the reason I'm discussing this particular case study is because it's sort of a breakthrough project for finite element modeling. So the Carsington Dam was built, or was analyzed in 1984, but it also failed that same year. So the initial slip factor of safety was about 1.4, and this was analyzed through the limit equilibrium method. However, the value was eventually reduced to 1.2 by the existence or by the presence of pre-existing shear surfaces, and ultimately the factor of safety was reduced to 1.0, and it failed. So why did it fail exactly? So the initial failure was partly due to pre-existing shears formed by periglacial solufluction in the natural ground. So essentially what happened was in the region in which this dam was constructed, periglacial solufluction was a variable that needs to be taken into account. So essentially what periglacial solufluction is it's when water is periodically frozen, melted, and then refrozen. So if you can imagine, say the water level was around here for this dam. Just imagine the water being frozen at one point. And as we all know, when water freezes, it expands. So when that water in the soil expanded, it caused additional shear. And then ultimately it melted, causing additional shear. And now this happened over the course of, I believe, several months. So over time, the shear stress became too much for the slope, and it led to its failure. So then as engineers were studying why this dam failed, and once they discovered periglacial solufluction was a major factor, they realized by using finite element analysis, the mechanism of failure could have been accounted for. So something that's very unique about finite element modeling is that you can take shear stresses due to poor water pressure, or for example periglacial solufluction in this case, into account. So that's sort of one shortcoming of the limit equilibrium method, is that it assumes, for example, that the water level will stay the same and that there aren't any internal shears caused by periglacial solufluction or any other factors. So once engineers realized that finite element modeling can account for these sort of factors, it started to take greater precedence. More engineers started using it for their analyses. So this is just one of many sort of instances in which finite element modeling was shown to be a very valid and a very useful solution. Okay, so what exactly can we obtain from numerical analysis? As I said, deformation can be obtained. This includes settlement and horizontal displacement. So if you look to the bottom here, here we have sample, sort of a cross-section of a 3D block of soil and the ground deformation. So if you see the areas in red, it just immediately shows you certain points that may be certainly like maximum deformation or points that may be of interest to you. Same with the failure area of soil. So try to imagine just trying to do a project like this with maybe a conventional method. So you have like a large spreadsheet with all these different numbers, and it'd be sort of, and there's a certain maybe type of value range that you want to find. It would take maybe a couple of minutes or maybe even longer for you to find that value range just looking through the spreadsheet. But with numerical modeling, you're able to see the range that's of interest to you just at a glance. So these models both correspond to maybe like a spreadsheet that would maybe have hundreds and hundreds of different values and coordinates, etc. As you can see, it's much more convenient to just have a contour model such as this. So with numerical modeling, you're able to calculate, you're able to develop or generate models that are very convenient, that are very in-depth, and that are very detailed in their results. And also, factors of safety are automatically calculated with numerical modeling. Now for structures, so the same principle holds true for structural elements. So here we have examples of two structural elements that were used in the numerical modeling project. As you can see, they both have contour graphs. This one represents the bending moment. So you can see at a glance, you can find areas of sort of maximum bending moment, and you can see where, maybe the bending moment would change over certain points, or areas that may be of interest to you. And once again, this is much easier than having to go through a large spreadsheet or having to go through various hand calculations. With numerical modeling, you're able to get large quantities of results that are very organized and that are very clear and concise within a very short period of time. And then here we have the axial forces for a group of pile elements. So as you can see, the program clearly delineates axial forces that reach a certain range. So as you can see, these piles here to the right might be of interest to the engineer who's studying it. You might want to see why exactly those piles receive X amount of axial force as opposed to these ones. So this works for 3D geometry as well. So as you can see, for larger, complex projects that require a lot of data and a lot of analysis, numerical modeling is especially useful. But even for smaller scale projects that have that you can do with conventional methods, you still might be able to find certain factors that may be of interest to you that you wouldn't be able to find through conventional methods. So it has numerical modeling has very valid and very useful functions for both large and small-scale type projects. Okay, so how to utilize your design parameters. So these are things that we need before we create our numerical model. So first and foremost, we need our drawing. Obviously, these are typically done in AutoCAD, and you just need to make sure what sort of drawings or project geometry you need to take into account for your project. And also your soil profile. So this should look familiar. You should need to know what sort of soil you're dealing with, the profile or the soil strata. So how deep each layer is. And you need to have your soil parameters ready and at hand. And then for the drawing. So first you need to decide the type of model you want to create, a 2D view or a 3D view. So 2D and 3D modeling, each of which has its own sort of benefits. So it really depends on the type of project that you're running. So for example, with a 2D project with simpler, more straightforward geometry, a 2D analysis would be best because it simplifies things to a point where you can work more efficiently. But for larger scale projects that have maybe complex geometry that absolutely has to be modeled in 3D, then 3D modeling would work best so that you could take all of those variables into account. So we'll discuss sort of deciding between 2D and 3D modeling later on in our courses, but just keep that in mind that there are two sort of main types of numerical modeling, 2D and 3D. And it really depends, it's really on the engineer to decide which one is best for his or her project. Okay, then the level of detail. So as you can see to the right here, this is a very sort of detailed drawing. But as far as your numerical model, there may be certain things that you want to omit just for the sake of simplicity. So for example, if you have a type of project that we would need an interface or a soil structure interaction type project, you would definitely need to get the interface between the soil and the wall. You need to consider bonded parts. And then say, for example, an angled backfill. So this is something that would definitely need to be taken into account because the soil pressure would be sort of different because of this angle of the backfill. So once again, with a conventional method, this would be a little more time-consuming to model, although you'd be able to get a result with it. But with numerical modeling, you'd be able to model this much faster. And then also the type of analysis and the application of the elements. And as we we'll be discussing more of these two sort of parameters in greater detail. Okay, so soil profiles. So I'm sure you all are familiar with these types of soil behaviors, characteristics. So for example, is it cohesive, is it granular? Also you would need your SPTN values, your consistencies, your angle of internal friction, which is especially important for foundation type projects or pile foundation projects, etc. So it's very important just to have all of your data at hand and ready for you before you run your numerical model. Okay. And other things to be considered in your numerical analysis, your geometry shape, the shape of your structure, how you want to create it, how you want to model that geometry into your numerical model itself, etc. Input parameters, so soil parameters that I mentioned, boundary conditions, and analysis options. So as far as boundary conditions, we'll discuss those in greater detail later on, but it's essentially what parts of the project site you want to take into account during your model. Analysis options, as I discussed, there are certain projects that require various analysis types. So depending on what the client is wishing for the project, what he or she wants to account for, then there are certain analysis types that you would need to take into account. And when these analysis types are interlocked or are interrelated, then it really becomes important to decide what order the analysis is run. And numerical modeling has an option called coupled analysis which is especially useful for projects that require multiple interrelated analysis types, and we'll discuss that in greater detail. And then engineer's knowledge. So it's really important that as an engineer you feel you have all the knowledge or all the project data ready and available to you, that you understand the project scope as well as any type of conventional or numerical modeling methods that you're using. Okay, so the geometry shape. So once again, 2D versus 3D. So depending on the geometry of your project, you need to determine what type of model you want to create. And then, another important thing to realize is that sometimes engineers, once they find out they have the ability to model in 3D, they just immediately maybe want to start modeling all of their projects in 3D, which is typically not a good rule of thumb, because there are certain projects, as I said before, that are more straightforward and simple, and they can be done much faster on a 2D platform as opposed to a 3D platform. And as we discussed earlier, we'll be discussing more of this sort of criteria and what to take into account when selecting your model type later on, when we start doing our sort of live demonstrations of numerical modeling programs. And then boundary size. So as I discussed, it's related to the efficiency of the analysis. So for example, take a look to the right here at this image. As you can see, this is a 2D excavation type project, and the depth of the excavation is labeled by DC. And then all of the other boundary conditions are a function of D, or the depth of the excavation. So we'll discuss sort of how to select your boundaries a little more later on, but just keep in mind that you want to make your boundaries to a point where you include all of the area sort of around the area of interest, but you also wouldn't want to make it so large that your analysis would run longer than it should be. And we'll discuss and we'll give very detailed instruction on how to select your boundary conditions when you're running your numerical analysis. So yeah, boundary size, if you choose just the right boundary size, then your model should run very efficiently, whereas if you use a boundary size that's either too big or too small, then you could run into certain issues. And then shape of the structures, that's pretty straightforward, just the geometry of your structural elements. And then soil strata, it's very important to have all of your soil data ready and at hand and to model all of those soil layers correctly. So input parameters, garbage in, garbage out. So this is a very important principle of numerical modeling. Essentially what it's telling us is that if we have, for example, an analysis that we ran and we have data or post-processing results that doesn't make any sense, that just seems useless, essentially what that means is that there was a problem in the input. So if you have a project where you inputted maybe a parameter incorrectly, or say you got mixed up with the units or something, then you're going to get an output data that's not going to be consistent. That's not what you expected. So that's an important thing to remember. The way that I like to think about it is just through, for an example, an engineer is only really as good, or the software is only really good as the engineer who's using it, or a car is really only as good as the driver who's driving it. So for example, you could have a really great car that's very well made, but if the driver is inexperienced, then the performance won't be as good as you would expect. The same principle applies to software or any type of numerical analysis. Although numerical analysis in and of itself is sound, if it's used improperly or incorrectly, then the results won't be up to par. So it's really important to remember to try to take accountability. If you have, for example, a numerical analysis result with results that aren't what you're expecting, or if you're having trouble with it, then you just need to go back and check the input. It's nothing really wrong with the program itself. Okay, and as I said, in order to ensure a good analysis, you need to have your soil parameters ready and at hand. And so it's really important to have all these parameters not only ready, but to make sure that they apply to your project site, that you have the parameters are accurate and that are reliable. And then boundary conditions, I won't go into too much detail, but these are constraints that you'll be using. Hinge, roller, fix for your boundary conditions, and for seepage and seismic analysis, you'll be using these parameters here. So whenever you're running a seepage or a seismic analysis, just make sure to have these parameters ready. And then as far as analysis options, the two main analysis options that we'll discuss, or the two main ones that are of interest, are drained and undrained analysis. So for example, for a drained analysis, you'd only need to concern yourself with effective stress and long-term stability. But for an undrained analysis, where pore water pressure needs to be taken into account, then you also have to account for the total stress and short-term stability, because as I'm sure you all know, undrained soils tend to behave very differently. Okay, engineer's knowledge. So certain things that you need to ask yourself before you run your analysis. Do I understand my tool correctly? If so, then you won't have any technical problems. Something that I've learned and understood over my time as an engineer is that typically any type of technical problems are due to a lack of understanding of the tools that are being used. So if you're having issues with your your analysis, just try to go back, look at your inputs, look at what you're doing, and try to understand your tools better. Do I assess input parameters based on geotechnical knowledge? So once again, it's very important to understand all of your input parameters to realize what those numbers represent. Because if you understand sort of the theoretical background or the theoretical principles of those numbers, then you'll be able to avoid any type of costly mistakes. So it's one thing to see a number, but it's another thing to understand what that number represents as far as geotechnical parameters. And then, can I explain the result behavior in a geotechnical way? So it's very important to understand the correlation between physical results of numerical analysis and geotechnical behavior. So essentially what this is talking about is the importance of interpreting results so that everyone can understand. So for example, as an engineer, you'll be able to develop an understanding of numerical analysis that might be hard for other people to interpret, for example, a client or a contractor. So it's very essential to be able to explain the results of numerical modeling or even conventional analysis to other people who are involved who don't have that frame of reference, who aren't engineers. And we'll discuss more in detail how to interpret the results of your post-processing later on and how to explain these results so that everyone involved in the project can understand. And then, can I define the reliability of the results? So numerical modeling and conventional methods, they're very powerful, but they're not perfect. We're still sort of striving towards greater solutions as engineers and as an industry as a whole. So just realize that even though you have maybe results that are good, that are favorable, there might be certain things you're not taking into account, and there might be certain things that you need to consider as well. So just understand that the results that you get through your calculations, they're really just estimates. They're not. Then you need to define how reliable those estimates are. Okay, and then just a summary of the second chapter. Always think, why am I doing this analysis before you build a model? So always keep that end goal in mind. So, for example, I'm sure whenever you begin a project, the client will list certain things that he or she wants, and then just sort of link those goals to the beginning, to why exactly you're building your model, why you're selecting these analysis types, etc. I found over my experience as an engineer that as I've continued to be more goal-oriented, I've been able to work more efficiently and to do projects at a pace that works towards completing that goal that were outlined at the beginning. Interpret analysis results properly. So we'll discuss more about result extraction later on, but it's very important to understand, what the numbers mean, what they represent, and it's really important to be able to explain them to others. Numerical analysis reflects the design process. So you need to utilize your design materials and find correlations. So there's certain relationships between numerical analysis and the design materials themselves, and we'll go into greater detail later on as these sessions progress on what these relationships mean for your project. And do not forget garbage in, garbage out. So as you're starting with numerical modeling, at the beginning you might have results or you might have certain issues with results, or you might not understand exactly why you're getting those results. It's really just important to start to go back to the beginning, look at your input parameters, look at what you have in hand, look at the way you model the project. Whenever you have any issues with a program or with your analysis, if you just go back to your methodology, what you put in, you'll always be able to find something that needs to be changed in order to get a desired result. Okay, so now I'll just take a quick breather. I'll give you another quiz. And once again, it's just another 3 questions, multiple choice. It shouldn't be too difficult, and as I said, I'll give you guys 5 minutes, which should be more than enough time to complete the quiz. So just give me a second here, and I'll pull it up for you all. Okay, so once again, the 5 minutes is plenty of time. Just take your time, just read each question carefully, and just submit when complete. Okay, so I see everyone has submitted their test, so let's move forward now. Okay, so Chapter 3. Now we'll be discussing the importance of soil parameters, certain parameters or certain unique characteristics about soil that make numerical modeling sort of essential. Constitutive models, various models that predict soil behavior that will be at your disposal, and also various analysis types for solving geotechnical problems. So the definition of a soil parameter is simply a physical characteristic for a soil to reproduce the ground behavior mathematically. So it's essentially certain equations or relationships that have been developed mathematically to help you better predict how soil will respond under certain stimuli. So types of soil parameters. First, let's talk about natural soil parameters. Parameters such as unit weight, relative density, void ratio, water content, consistency, liquid limit, plastic limit. These are all parameters that you should be familiar with, and then you should have all these parameters ready for you when you create your numerical model. And these parameters are essentially used for all types of geotechnical analysis. And then stiffness, for example, elastic modulus and Poisson's ratio. So these are essential for calculating, for example, deformation. So it's important, for example, maybe like a retaining wall project or excavation type projects where deformation is studied a lot. Then elastic modulus and Poisson's ratio are very, very critical. And then strength, such as cohesion and friction angle, these are typically used for deep foundation type projects or pile foundation projects. So just make sure to have your database ready. And then seepage analysis, permeability, and the soil water characteristic curve. So these are all parameters that are essential for seepage analysis. And then dynamic analysis, the shear modulus, and the damping ratio. So just make sure before you run your analysis or before you create your model that you're familiar with all of these parameters and that you understand what each one means, and then also why it's important to the particular analysis type that you're running. Okay, so characteristics of behavior. So we'll discuss the decision of the parameters as well as strain-dependent and stress-to-path-dependent behavior, which is a very sort of unique characteristic, sort of a unique variable that needs to be taken into account during geotechnical analysis. So first let's discuss just nonlinear behavior of soil. So an important thing to note is that this test has been run for the same type of soil 3 times. So as you can see, each time the result is different, and each time the result is nonlinear. So in other words, the axial strain will increase linearly, the deviatoric stress will increase linearly with axial strain up to a certain point, and then it'll start to taper off and become nonlinear. This is sort of what makes geotechnical analysis very tricky for soil parameters. So one of the main things to sort of get from this is that soil behavior is complex and requires nonlinear behavior to be taken into account. So as you can see, based on the type of study we want to create, if we get the tangent, secant, tangential, or initial, we'll get 3 different values, all of which are very different. So it's really up to the engineer to decide what value he or she wants to use for his project. For example, if you're doing a very conservative type project, where project cost wouldn't be harmed by an over-conservative design, then you could use, for example, your E initial. But if you're running a more conservative project where a more detailed or a more accurate analysis would be required, then you could use E tangential or E secant. So it's really up to the engineer's discretion. So that's sort of one of those complexities of geotechnical analysis, is that there's no real sort of obvious way to do things. You really need to understand your soil behavior first, as well as your project scope, and then based on the needs of your project, you would choose the parameter that best suits what you need. Something that's very unique and useful about numerical modeling is that you would be able to create a design or an analysis taking all 3 parameters into account if you were to run a parametric study. So that's where the root parametric comes from, just various sort of standards. Okay, and the same principle applies to strain-dependent behavior. As you can see here, the shear modulus also behaves non-linearly. The shear modulus as well as the shear strain, Okay, so now stress path dependent behavior of soil. So let's take a look at this first image here. This is just a sample of an embankment type project. So the soil is uniform across the length of the embankment. However, the stress curve or the stress path is not. So as you can see, the soil, depending on which location under the embankment it is, will receive a different stimuli. So for example, here, as you can see, the loading is axial, in which case we need to do the triaxial compression test to calculate or to predict how the soil would react. In this case, there's a shear going across the top, so we need the direct simple shear test to analyze or to calculate how the soil would react. And then last, in this part of the soil, the loading is being applied laterally, which would require the triaxial extension test to determine how the soil would react to the strain, how it would compress, etc. So as you can see, it's a very sort of simple, straightforward project, but because of the stress paths and the nonlinear behavior of soil, you would need 3 different tests to analyze how 3 different sections of the soil would react. The same principle applies to loaded walls. As you can see, you'd require a direct simple shear test as well as a triaxial extension test, simply because of the way the stress path moves across the soil. Vertical walls are fairly simple. You can do the triaxial compression test. But then for drilled shafts, once again, that same principle applies. So you'd need, depending on how the load's being applied, whether it's axial, whether it's pulling up as an uplift, or it's lateral, you'd need a different combination of these tests to really get an analysis of the soil that you could be confident with. Okay, and then here is just another sort of illustration of how how the same soil is being put under different tests. And as you can see, each result is different for each test, and then each result is nonlinear. So as you can imagine, for projects in which soil behavior analysis is essential, it can be very complex. But with numerical modeling, you'll be able to use all of these tests, and they'll all be at your discretion, all these parameters. Numerical modeling provides you with a tool that can help you to better analyze soil behavior, because as engineers all know, soil behavior, depending on the type of soil you're working with, can be very sort of difficult to calculate, and you really need to understand just these tests and how that soil behaves in order to really predict with confidence how it will react under certain stimuli or under certain project changes. So rock behavior, on the other hand, is linear. It's very predictable. So as the strain increases, the stress increases linearly. So that's one of the main advantages of working in rock foundations. One of the disadvantages of working in rock foundations is just the scope of having to remove it, having to excavate it. That's very difficult for contractors. But as far as the sort of design angle, rock is very sort of reliable. It's linear. But there are certain times when rock layers and soil layers are used in the same project site, in which case you need to account for both linear and nonlinear behavior. And then just to discuss more about nonlinear behavior of soil. So there are 2 sort of main ways the soil can behave nonlinearly. First, let's discuss strain hardening. So as you can see, as with the other examples I showed you, the response will be linear up to a certain point, and then it'll start to taper off in terms of strength. So essentially, this applies to soils that have loosely packed grains and strain hardening. And packed grains are strain hardening because the disturbance during sharing causes the grains to move closer together. So in other words, the reason the soil increases in strength so much at the beginning is because all the grains are compacting. But later on, as more and more strain or more and more load is applied, there's less compaction to be done, and that's why the hardening sort of tapers off. And this typically applies to like weathered rock type soils. And then strain softening. So once again, the behavior will be linear up to a certain point when it reaches the elastoplastic range, at which points this is called the yielding area, and then it'll start to soften. The soil will actually start to weaken as more and more load is placed upon it. This is sort of a critical area that needs to be taken into account. So whenever you have sand or clayey soils, it's very important to account for this behavior, to account for a portion of which, to make sure that you can account for the behavior after the loading reaches a certain point where the soil will start to weaken. that accounts for a lot of settlement. So for example, for alluvial layers such as sand or slowly consolidating layers such as clay, this behavior becomes more and more prevalent. Okay. Now we'll discuss various types of analyses for solving geotech problems. So these are the 6 main types that we'll discuss, not only in this section but in the course as a whole. So I'm sure all of you took a look at the course schedule. Later on, what we'll do is we'll have a session dedicated to each analysis type. So for now, what I'll do is I'll just provide a basic introduction to each. So first, let's discuss static analysis. So one of the main characteristics is that it's a final stage analysis without construction stage. So for projects that don't have complex constructions or excavations, what you can do is you can just model the complete project itself and just analyze the effects of the loading on your soil. You don't have to consider in situ stress or soil pressure. It's a simple analysis, so it's very easy and it's very fast. And it's similar to the analytical method as far as numerical modeling is concerned. And then self-weight of the soil in a semi-infinite elastic medium is 0. So if you look at these 2 images here, this is just a finite element model. And as you can see, all of the results have been put upon this graph here. So what we have here is the stress for the soil, both in analytical and program terms. So these triangles represent what the program or the numerical modeling program has generated as far as results. The squares represent those results as well. And then these lines represent the results given through the analytical method. So since static analysis is fairly simple to run, it's always good to have your results checked against each other. So in other words, if you have your numerical analysis and you get a certain set of results, it's a good practice or a good rule of thumb to run your analytical analysis to make sure that your results are along the same lines. So as you can see, this would be passing because the analytical and the numerical modeling results are roughly along the same lines. So there isn't too much separation between the 2. Okay, and then construction stage analysis. So these pictures just sort of demonstrate a sample of construction stage analysis. This is actually a case study that we'll be discussing in further detail later on. But the main things to remember about construction stage analysis is that it takes large, complex projects that require extensive amounts of time to construct, and it simplifies them by separating them into certain stages. So as you can see, even the excavation itself, the layers were separated, and then later on during the construction of the basement foundation, the piles were separated. The basement layers were sort of separated into different stages. So later on, when the analysis is complete, you can combine all of these stages to get a really detailed understanding of the effects of the excavation and the construction on your foundation and the adjacent structures. And as we discussed earlier, construction stage analysis is very difficult to cover by the analytical or the empirical method, simply because it requires a lot of repetitive steps. But through numerical modeling programs or techniques, you'll be able to have a certain set of input parameters, and then just through manipulation of these parameters over several stages, you can create dozens of construction stages very efficiently. Okay, and then seepage analysis. So determining the groundwater level, for example, how your groundwater level changes, maybe due to certain factors such as rainfall or an increase in head. Estimating the flow or the flow path. So as you can see, numerical modeling, you can estimate your flow, or you can graph your flow paths fairly easily. And then evaluating piping potentials, hydraulic gradient, flux. So these are all things that need to be taken into account for seepage analysis. And typically dams, embankments, levees, structures of that nature would be analyzed through the seepage analysis. And then for more advanced analysis options, such as, for example, rapid rainfall or rapid drawdown. So say, for example, I had a dam and I wanted to model different degrees of rainfall because this dam was in a very high precipitation zone. I could do that through numerical modeling, and I can get various cases that show how the pore water pressure changes as the head increases or as it continues to rain. Same thing applies with rapid drawdown. So for example, if I were to empty this basin very quickly, a very fast and rapid change in pore water pressure would cause a certain amount of weakening and shear stress in the slope, and I'd be able to analyze that with a numerical modeling program as well. So yeah, just keep in mind that with more advanced analyses, numerical modeling is especially useful because with conventional methods, you could do them, but it would take much longer. It would take use of extensive amounts of spreadsheets. Whereas with numerical modeling, all you need are your parameters, your model, and you can be able to create or to do these sort of calculations in a very efficient manner. Okay, so slope stability analysis. We discussed the limit equilibrium method. It's the most commonly used method because it's very easy to use. Many engineers are experienced with it, and it's very efficient for simple sort of steady state problems. The strength reduction method is how the finite element analysis calculates slope stability. So it calculates the factor of safety, but in addition to that, it also considers deformation as well as field conditions such as stress history or construction stages. Also, if you were to have like soil reinforcements or a retaining wall built into your slope, the finite element analysis would be able to take that into account as well. And then also 3D slope stability analysis. So for example, if we were working with a slope with asymmetric 3D geometry, so for example in the lateral direction it's not uniform, then a limit equilibrium method might not be your best choice of best analysis method, in which case you would need to run a 3D slope stability analysis using the shear strength reduction method just so that you could take into account the asymmetric geometry. And then for advanced approach, a seepage slope coupled analysis. So for example, for a levee, if you would want to analyze the effect of pore water pressure on your slope stability, then a coupled analysis would be ideal. Okay, seismic analysis. So seismic analysis criteria, for example, dimensions. So seismic analysis also has 1D ground response analysis, which is essentially used to analyze how your ground will respond under seismic loading. And then 2D and 3D soil structure interaction analysis to analyze how your ground would respond to seismic loading when pressed up against, when in direct contact with a structure such as a foundation. Domain, time, and frequency. So we'll talk more into sort of 2D response analysis later on, as well as time history analysis. But time is a very important sort of factor to take into account with seismic analysis. And then the stress-strain relationship. So for linear behavior, you only need to worry sort of about the elastic range. In other words, the range in which soil would retain its original shape after being exposed to an external stimuli. But then for nonlinear behavior, you'd need a more detailed analysis. And then excess pore water pressure. So when groundwater levels are taken into account for a seismic analysis, you would need to account for effective stress as well as liquefaction, and then total stress to analyze certain parts that don't have groundwater present. So these are all things to take into account for seismic analysis. I won't go into too much detail yet, but later on, as we do, I believe one of our courses is dedicated to seismic analysis. We'll go more into detail on how these parameters are used specifically for numerical modeling. Okay, so coupled analysis. So essentially what coupled analysis is it runs analysis that have overlapping domains. So one of the examples is seepage through a porous medium with a dynamic or structural behavior. So let's take a look at this image here. So say for example you have a dam with a steady state water level. There's going to be seepage on the other side. So you need to run a seepage analysis to see how that would affect your dam. But also say you have a consolidating layer. Since the pore water pressure is going in the vertical direction, that's going to put less pressure on the consolidating layer, which is going to affect your eventual settlement. So essentially you'd be running seepage analysis as well as a settlement analysis. So in order to simplify things, you could just run a coupled analysis with numerical modeling. In other words, you could run your seepage analysis and you can directly import your pore water pressure loads into your settlement analysis, which is especially useful because with conventional methods you could do both, but it would take longer because it's not using sort of the same analysis methods. It's not using the same platform. The same principle applies to deep excavations. You need to run an analysis for the stability of your supports or the ground in general, as well as how the pore water pressure would affect that. Same with retaining walls and tunnels that are exposed to groundwater. So we'll go more into detail about coupled analysis, but just keep in mind that it's very effective for seepage type problems where structures where a structural design needs to be taken into account for the poor water pressure of the water. And then problems with coupling via interfaces, so for example the retaining wall that I mentioned, and then fluid structure interaction, so structures that are in direct contact with water, and then structure to structure interaction, so for example certain structures that interact with each other directly would benefit from a coupled analysis. Okay, so I have one last quiz for you. Once again, it's 3 questions, all of which are multiple choice. You'll have 5 minutes, so feel free to just take your time and to read each question carefully before selecting. So now let's move on into the final chapter, and that was the last test, by the way, so you don't need to worry about another quiz. So let's go into the last chapter, which we'll be going over just a couple of case studies in which numerical modeling was used efficiently to solve certain geotechnical problems and overcome certain obstacles. So we'll go over a pile foundation, a deep excavation, as well as a ground settlement project. So first, we'll discuss the Pentaminium Tower in Dubai. So as you can see, this is a rather large-scale project, high-rise building, and also another sort of layer of complexity was the geological cross-section. So as you can see, there are various stone types as well as sand types that need to be accounted for. So nonlinear as well as linear behavior acting against the piles would need to be calculated. So numerical analysis was used to evaluate the overall pile draft response under various static and wind loading combinations. So because of all the different loading combinations, numerical modeling was especially useful to just take all of those into account. Also, there are some techniques used to optimize the foundation design, including the preliminary design testing. So in order to optimize the design, a parametric study was performed in which several different variations of pile configurations were tested, not only for safety, but also for economy. Okay, so here's an example or a picture of the finite element model itself. So as you can see, it included 9 levels of the superstructure as well as 6 basement levels. And the settlements obtained from different types of soil, both linear and nonlinear. So as you can see, the pile configuration was very complex and needed to be modeled in 3D. And also because the project had various construction stages, a staged excavation and a staged construction models were created as well. So just using finite element modeling, they were able to take a very large, sort of complex project and break it down into smaller, simpler pieces that were more sort of doable and more efficient to run. And then also, this is just sort of a graph of the soil behavior. So as you can see, the nonlinear soil behavior, there was much more deformation and settlement to take into account. Whereas with linear soil, less deformation is needed to be taken into account. So a substantial amount of testing was carried out for the design of the Pentaminium Tower foundation, which included soil and rock testing as well as a comprehensive pile testing program, which the numerical modeling program was able to contribute to. In addition, complex geotechnical finite element analysis was carried out, which had been validated using standard geotechnical calculations. So the application of such testing and analysis approaches has resulted in a very cost-effective and optimized foundation design solution. So that's one of the main things that I want you guys to get from this presentation in general, is that through numerical modeling you'll be able to find more cost-effective solutions. So for larger scale projects, becomes more and more important to take design costs into account. So for example, by cutting down maybe a number of piles or using a certain type of element over another, you could save hundreds and thousands of dollars just because you took the time to maybe do a parametric study instead of going with a more conservative design. So just keep that in mind as well, that numerical modeling is not only useful in sort of the calculating sense, or the physical sense of calculating your results, but also in the economic sense as well. Okay, so now let's go over this the Louisiana Bulkhead project. So for this project, the client was responsible for the Louisiana Seaport Bulkhead. So the ships would be transported from the warehouse to the shore via sort of this rail system. So because of the unstable ground conditions, the consultant decided to place additional piles which are necessary to improve ground conditions. So the new adjustments took into effect the settlement, and through numerical modeling, or the program itself was able to analyze the ship load through modeling point loads, and we'll discuss more about the different loads you can model with the program later on. Oops. Okay, so this is an example. This is a sort of an overhead view of the pile configuration. So as you can see, the pile configuration was very complex. It required dozens of piles, and because of the complexity of this project, the numerical modeling program was opted to be used. So let's take a look at the model itself. So as you can see, the modeling itself was actually done section by section. So the initial modeling began with the piles, and the surrounding structures were modeled first. Then the soils were modeled subsequently with the proper material properties. And finally, the last steps were to create the top layers and the rail tracks themselves. So just as you can see, the model needs to be created in 3D because of the geometry, and then also because of the complexity of the project, section by section, it was created section by section. So as you can see, the piles were created first with the geometry, then these transparent boxes here represent the soil layers, and then eventually the sort of superstructure, or the foundation parts, were introduced as well. So this was a large-scale, sort of complex project, but through numerical modeling and construction stages, they were able to break it down into simpler pieces, which made the project much easier to undertake. Okay, and here's just a couple of views of the post-processing models. So here's the cross-section of the stress model. So as you can see, at points where the point load was applied, there's more stress. So that hence this area here is colored in red. So using the numerical modeling program, you can just see sort of at a glance certain areas that may be of interest to you, certain areas where values are uniform or more linear. Same applies to the displacement value. You can also get a deformed shape. That's obviously exaggerated, but you can see sort of at a glance which piles would experience the most displacement or the most deformation. So for a project with this size and this scope, you'd have large amounts of data, but you're able to have all that data just very easily and accessible to you just through importing it into these post-processing model files. And then later on, once you're preparing your final report, you can just export the results for a specific region. Say, for example, I just wanted the results for this region because I thought it was a critical region that would need to be sort of accounted for. I could export all of those results, and I could study them in greater detail in an Excel spreadsheet. And we'll discuss more and more about how to interpret results in later sessions. Okay, so then the Odean Tower, which is a high-rise 49-story tower in Monaco. So it included an assessment of ground surface movements, especially at adjacent buildings. For example, as you can see, the area itself is very developed. So in order to create the excavation, or to design for the excavation, the effects of the excavation on the adjacent structures needed to be taken into account, especially for arching effects on the uphill side. So as you can see, we already discussed this particular project in the previous session, but I'll just go into a little bit more detail here. So as you can see, there was an adjacent building foundation that needed to be taken into account, a retaining wall, a street, etc. So just through dividing this excavation into various stages, they were able to see sort of step by step how the soil, or how the nonlinear behavior was affected by the excavation of the foundation. And eventually, they were able to model the foundation itself. So they're able to analyze or to design for the slabs that enclose the diaphragm wall, the piles themselves. Once again, the project geometry was very complex and asymmetric, so it needed to be modeled in 3D. They were also able to design for the cable anchor system. So there were many variables that needed to be taken into account for this project because of its size and its scope. And through numerical modeling, they were able to sort of break it down into simpler steps, and they were able to take all these variables into account. So they're able to design for each phase of the construction. So one of the main things that I want you to sort of get from this presentation is that numerical modeling is very sort of wide-ranging. So the case studies that I just showed you are for high-end, very complex projects. But also keep in mind that numerical modeling could also be used for smaller-scale conventional projects as well. Projects that you'd maybe do more regularly than these. These are sort of an atypical sort of project type. So for example, for smaller pile foundations that need to be modeled in 3D, this one's much more straightforward and conventional, and could be modeled in a much faster time than the previous projects. But you'll be able to analyze both the structural effects as well as the soil element effects. So just using numerical modeling, you could separate the project. You could do soil structure interaction to get the displacements, the stresses. You could design for this 3D geometry, and you could also design for, or you can also account for the effects of settlement due to your foundation and the excavation. And then also seepage analysis. This is a very straightforward, conventional type seepage project, just a very simple embankment. So the water level would be resting on this side of the dam. So here the head would be larger, and then as you go to the right, to the empty side of the dam, the head would decrease. And also you'd experience a great amount of seepage and a hydraulic gradient. So through using numerical modeling, you'd be able to get your flow nets as well as your hydraulic gradients. If you double click on those arrows, you'd be able to get specific values for flow volume, flow velocity, etc. So instead of using a conventional method, maybe drawing this out or using hand calculations, it would be much more convenient to do this project on a numerical modeling program first, and then choose certain specific sections that you'd want to calculate with conventional methods, and then check those answers against each other. So once again, with numerical modeling programs, you can supplement sort of the tools and the skill set that you already have to work even more efficiently. And then last, just a very straightforward slope stability project. So as you can see, because I modeled this project with a limit equilibrium method as well to get the factor of safety, but because it had certain soil nail reinforcements, also known as tiebacks, involved, I decided to run a strength reduction method just so I could check the shear stress. So as you can see, the stress pattern changes because of the presence of these tiebacks. Also maximum principal stresses, minimum stresses, shear strain, etc. So I was able to get all of these values, or excuse me, this is the lateral displacement, and this is the shear stress. So I was able to get all of these values just through using numerical modeling. So I was able to do one analysis, but through the finite element method, I was able to obtain all these different sort of calculations, all of which were variables that the limit equilibrium method couldn't take into account. So as I said in the beginning, it's always best to have a different sort of combination of analysis methods at your disposal so that you can account for all variables. Okay, so this concludes session 1. Next week's session will be utilizing numerical analysis for foundation design. So we'll get, this session was really just more of an introduction to what we'll be going over in the next 7 sessions. So next week's session will focus specifically on foundational design and how numerical modeling can help you get certain special solutions, how it can be used to supplement certain design methods that you already have. And then also what I'll be doing later on today is I'll be sending you all information on how to download free trial versions of Midas GTS and SoilWorks. Those are 2 of our numerical modeling programs. That way you can download them, and then you'll be ready for the assignments I will give out in the future, because later on we'll be giving out homework assignments where you'll actually get a chance to model certain projects on your own, so that you can see for yourself how numerical modeling can offer some unique solutions for you. So I'll get you the software download information by the end of the day. Okay, thank you for your time and your attention. If you have any questions at all about what was discussed, feel free to contact us at midasoft@midasuser.com. If you have any questions about anything specific, we can answer it for you. So feel free to send any queries to that email address. Feel free to call me. I know most of you should have my number by now. So thank you for attending session 1. Next week's session will be at the same time on the same day, so 3 p.m. Eastern Standard Time on Wednesday. And thank you again for your attendance, and we look forward to seeing you next week. Oh, and also I see a question here. So yeah, we'll post a recording very soon. So what I'll do is we'll post it probably on a site. So we'll send you the links to the site where you can view the recording as well. So if you have colleagues that want to see, or if you want to sort of review over the session, the link will be available to you soon. Okay, well, thanks again, and you all have a good day.